Welcome back everyone. In the last lecture, we had seen how to find out the Bode plot of a system if you know the transfer function of a system. We found out the steps that you can follow, and using that you can find out the Bode plot of a system. Today we ask the reverse question. What if you have a system with you and you want to find out the transfer function of a system? Remember, we have answered this question earlier also. Experimentally, you remember the motor experiment that we had done, where we found out the transfer function of a system using step input. Today, we will ask the question, can we find out experimentally the transfer function of a system using frequency response data? So, the idea is simple. If you have a system, give different sinusoidal inputs to the system. All these sinusoidal systems should have different frequencies. Collect the magnitude and phase of the output, and using that data try to find out the transfer function of the system. Let us see how we can do that. Suppose you ran an experiment and the data that you got was this, which is basically for different frequencies you got the magnitude in dB, scale. This was the magnitude, this is the magnitude plot that you got. How can you experimentally find this? As I have already said, you have to just give different sinusoidal inputs to the system, and based on that you have to check what is the output and measure the magnitude and phase. We will see soon in this lecture itself at the end that how to do that. Okay. Now, suppose I already have this data. Now, see what I can do is, looking at this data, I can fit an approximate Bode plot on this. Let us try to do that. So, you can see at the beginning itself, I can go ahead and fit a line of this form, say, because it says it can be considered as a straight line which is parallel to the x axis here or the omega axis here. Now, we know that when there is a straight line, the factor that contributes to a straight line parallel to the omega axis is the constant factor, which is k in this case. Then there is an increase in the output or in the magnitude. You can see that there is an increase in the magnitude, right? So, which means there is a slope change here, and I can fit in another line here which would be something of this sort. Again, remember, this is an estimate, it won't turn out to be the exact transfer function, it is just an estimate, and we are trying to get to that estimate. Now, you see, look at this line that I have drawn. So, at this point, so let me consider that this is minus 53. Okay, you can always get to the exact value. Let me consider that that is minus 53. Now, you can see that if that is minus 53, so from this point, so it is minus 50. So, at 10 to the power 1, this is somewhere here. So, there will be an increase of approximately how much? If you look at it, so this is approximately minus 50, and this is approximately somewhere around say minus 33 or 32, somewhere around minus 33 say. So, minus 50 to minus 33, which means approximately a 20 dB increase, right? Why I am going to 20 dB? Of course, it is not exactly 20 dB, it is somewhere around 17 dB or something, right? But I am telling 20 dB because I know that if there is a 20 dB increase, that means I know that there is a contribution of a 0 term there, right? We have seen this earlier while plotting the Bode plots. So, I can see that I can fit in a 20 dB line, approximate 20 dB line of course here, and that approximate 20 dB line will give me a factor. Okay. Now, what is this factor? Now, look at this point. So, what is the corner frequency here? Corner frequency is this point, right? If I am drawing the asymptotic Bode plot. So, this is somewhere around 0.8 say. Okay. So then I have the factor that comes is 1 plus j omega by 0.8. Now again at this point I can go ahead and draw another line. Now you see, so this was a plus 20 dB per decade line. So now it has become a 0 dB per decade line, which means there is contribution of minus 20 dB per decade, and we know that minus 20 dB per decade comes only when there is a pole contribution. And where is the pole? Pole will be at this location, and that is 1, right? And you see, therefore I have written 1 plus j omega by 10. So then of course this I am writing in anticipation of what is coming. So you can see that I can again draw another line, and this one is a minus 20 dB per decade line, again approximately minus 20 dB per decade line. You can go ahead and fit it much better, you can try on your own also. So you will see that this is somewhere around this point, which is say 48 radian per second. So this is the transfer function that I am estimating, that this is the transfer function of the system. It won't be the exact one, of course, because while I am doing these fittings, it might not exactly fit, okay, but to get an initial guess of what the transfer function is, this is what it is. Now I have to find out the value of k. You know how to find out the value of k. This k was coming because of this line, right? So what is that? So because of this line. So what is that? So therefore this point, which is minus 53 dB, so 20 log of k must come out to be minus 53, and which will come out to be k equal to 0.0022. So finally your transfer function will come out to be this. If the transfer function is this, I can go ahead and make it into in terms of s. So this will be the transfer function of the system. Now while doing this, so I hope this step is clear. Again, is this the exact transfer function? No, this is not the exact transfer function. This you have estimated. Now what will you do? Once you have the transfer function, you can now simulate this system, right? You can give different values, different inputs to this transfer function in the simulation world, and see what the output would be, and then carry out the same experiment on the actual hardware you have, and then match the magnitudes and the phase. If they are matching within some bounds, of course, within some tolerance, then you have the transfer function. If no, then you tweak the position of the poles and the zeros a bit to fit into that transfer function. This is how we can manually do this. Of course, nowadays, given the tools that we have, we can directly do this using software cell also, which we will see soon after I do this, okay. But manually, if you have no access to softwares, then you can directly do in this way also, okay. Of course, you have to log in all the data, do this cumbersome work of going through this entire thing, but it's fine. I mean, sometimes you might not have the software, so you can go ahead and do this, or you write down your own code, okay, to fit in the data. Whatever data you have to fit in to the magnitude plot. Now a very important point here to note is, when I said that the transfer function of the system is this, I made an assumption, okay. The assumption was that it is a minimum phase system. The meaning of a minimum phase system is that there are no poles or zeros on the right half of the complex plane. This assumption I had put. Of course, there cannot be poles on the right half of the complex plane, remember, because if poles are on the right half of the complex plane, the system becomes unstable. So that we will not consider anyways. But if zeros are on the right half plane, that is allowed, okay. When we talk about stability, we will talk about all these things also, right. So now why I am considering this assumption? Because let me just take this transfer function and plot the Bode plot for the case when there is a minus here. So as soon as it becomes s minus 0.8, you see that this has a 0 on the right half plane, right. So let me plot the two. So here are the two Bode plots, and this I have done in simulation, not experimentally. In simulation, I found out the two transfer function. Now notice the difference between the transfer function. The magnitude plots, there is no change, and why is that? You should understand why is that, because you see, if I have to find out the magnitude of this, so what is this? 1.32 j omega minus 0.8 by j omega plus 10 whole into j omega plus 48. Now what is the magnitude of this? The magnitude of this is 1.38 root over of 0.8 square plus omega square by root over of omega square plus 10 square root over of omega square plus 48 square. Where is the same thing if you do here? Here also you will get the magnitude plot to be the same, because this j omega minus 0.8's magnitude and j omega plus 0.8's magnitude are the same, because I am squaring it up, right? So the magnitude plot remains the same. And see, whatever we have derived now, just the transfer function that we have derived, we derived from the magnitude plot. So how do I make the difference? Is it this or this? Which is the correct one? Which is the correct transfer function? So in the previous example, I assumed that there are no zeros on the right half plane, so I said that okay, this is the correct transfer function, but it might not be so. Okay, so in that case, what will you do? Then you have to go to the phase plot. Look at the phase plot of the system. Okay, so first find out the transfer function of the system, considering that the system is minimum phase. So basically there are no poles on the right hand side, there are no zeros on the right hand side. Make that transfer function. Once you have that transfer function, now to be sure that this is the correct transfer function, you find out the phase of the, because you have measured it, right? You check the measurement of the phase. How is the phase looking? Because the phase of this and this will be different, because j omega minus 0.8, if you took a tan inverse of that, it will lie in a different quadrant, whereas tan inverse of omega by 0.8 will lie in a different quadrant, right? So j omega minus 0.8 lies in the which quadrant? On the second quadrant, right? Whereas j omega plus 0.8 lies on the first quadrant. So the phase will have a difference, right? And you can see that in the plot itself. Look at this plot and look at this plot. In both these plots, the phases are different. However, the magnitudes are same. So you need to look at the phase then. So let me just look at the data that I have, from which I created this. So I had this data. So let me just, so this is the code I am using. I had the data in this file. This is a CSV file in which I had captured the data, and now I am taking out the variables. So the first variable is frequency, the second variable is magnitude, and the third variable is phase. See, you can write these codes on your own in a different way also. Don't bother about how I am taking the data. You just must have the data in some format. Okay. Once you have that data, put it inside MATLAB or in other software. No need of MATLAB also. You can use some other software. Go ahead and plot the data. Let me just plot the data. So this part plots the data, and this is the magnitude plot, which was exactly similar to what I had shown. And look at the phase plot. The phase plot looks like this. So which means that if the phase plot is like that, then clearly this is the correct transfer function and we are fine. But if the phase plot would have come to be something like this, then you know that it is a non-minimum phase system and this would be the correct transfer function. Okay. So with one example, I have shown you how to do it experimentally. Experimentally as in how to find out the magnitude and the phase plots. You find out the magnitude and the phase plot somehow, and then you go ahead and do this analysis. You can find out the transfer function of the system. So what you have to do is you have to fit in, you have to take the magnitude plot, try to fit a approximate Bode plot on it, and then find out the transfer function of the system. That is the estimated transfer function. And then of course with experiments check whether your transfer function has to be changed a bit. So this will work as your initial guess, the transfer function which is your initial guess. Now the same thing, all the entire thing whatever I have just explained can be done in a different way also, directly using MATLAB, where we directly take the data and then feed in the data to find out the transfer function of the system. In the next video that I will show, you will see that how to find out the transfer function of the system experimentally. That also shows you how to find out the magnitude and the phase plot using a DSO. Let's have a look at that.
Hello everyone. So today we will be looking into the transfer function estimation of an unknown circuit using the frequency response of the circuit. So here we have a black box which consists of a circuit which we do not know about. So we are going to estimate the transfer function of this particular circuit using the frequency response of this circuit. So in order to do that, we will be providing sinusoidal input of various different frequencies from this arbitrary function generator. So this is the input side of the black box and this is the output side of the black box. So we will be providing sinusoidal input through the input side and we will be reading the output response of the system through the digital oscilloscope. So in the digital oscilloscope, now we can see a yellow line and a green line over here. So now in order to match the reference of the two channels, I will overlap the two and we shall see what the responses that we get. So now we shall start with a fairly low frequency. So here I'm going to give a sinusoidal input of 0.1 hertz frequency. So once I give the frequency, I give the input, the output of the circuit response can be seen over here in the DSO. So I shall increase the time scale so that we can see the response better. So here we can see that the input and the output response are almost overlapping each other. So we get a response of this manner for a low frequency, that is 0.1 hertz. Now I shall increase the frequency to about 10 hertz. Now when I apply a frequency of 10 hertz to the system, we can see the output like this. Now as I decrease the time scale, here we can see the change in the gain and the shift in the phase between the input and the output. So what we are going to do is we are going to log the input and the output data for the various frequencies, and we are going to use the log data to analyze the frequency response of the system in order to estimate its transfer function. Now in order to do that, we have to take this data in a storage device. So now I'm going to insert a USB device in the digital oscilloscope over here. Now in order to save the waveform data, I will go to File. Then here comes an option of saving the waveform. Now as I click over here, I have an option of naming the file over here. So I'll go to this, I'll go to file name, and then I have a small dialog box which allows me to write the whatever file name I want. So I'll clear whatever the default name is, and then using the cursor, I will write 10, which is the frequency for which I am recording the input and the output data. So 10 hertz, I will press enter, I will press escape, and then here is an option called save waveform. Now once I click this, the file starts to get saved. In this manner, we shall record the response of all the ranges of frequencies that we are providing as an input to this black box, and we shall record the corresponding output, and based on the response, we shall estimate the transfer function of this particular system.
We can see all the input and output data for frequencies ranging from 0.1 Hz to 10,000 Hz. Let us open the 0.1 Hz CSV file, and we can see the input and output data over here. Now we are going to create a single CSV file consisting of the input and output data corresponding to all the frequencies that we have measured. For this, we are going to copy all the data from each CSV file to a new file. We will also name the frequency for which the data belongs for future reference. For example, this one belongs to 0.1 Hz, so we shall write 0.1 over here. Now, after this, we are going to save this file, but we are going to save it in CSV format. To do this, we go over here and select the CSV UTF-8 format. We rename it as sweep data or whatever name you want, then we save it. We shall repeat the process for all the other files, 0.2 Hz, 0.3 Hz, and so on. We copy all the data from the individual CSV files and make one big CSV files so that we can import all the data at once. Now, these are the input and output pairs. We save this and close it. Once we have saved this, we'll go to MATLAB we will go to import data and we will select the CSV file that we have created. So wherever we have saved it, we will go to that location and we will select the CSV file, sweep data, and we can see a new window pop up like this. From here, we will click on import selection, and this will automatically select the data based on the available memory. And once we do the importing, we will get a table in the workspace. Now we want to save this workspace in a .mat file. We will use the save command for this operation. We will give the file name, whatever file name we want to give. In this case, let's keep it sweepdata.mat, and we will use the variable name over here, which is sweepdata1. In this way, we are going to save it. Once this command is run, we will see the saved .mat file. Later, we can reload the .mat file and we can see the sweep data in the workspace. Now, we will run a code to specify all the frequencies for which we have taken the input and output data and calculate the gain and the phase difference between the input and the output. Once we run this code, all the gain data and the phase shift data will be populated in the workspace. Then, using this data, we will be estimating the transfer function of the unknown system. The code for transfer function estimation is given over here. Once we run this code, we can see the estimated transfer function based on the frequency data that we have collected. Here is the estimated transfer function. We have used the TFEST function. So this is the plot of the experimental data that we have collected. The top plot is the gain plot and the bottom one is the phase plot. Now, since we have the estimated transfer function, we must verify whether it is correct or not. So the black box that we have used consists of an RC circuit with the R1, R2, C1 and C2 values as given here. So the theoretical transfer function calculated based on the values of the resistors and capacitors are shown here. We will do a comparison run between the estimated transfer function and the theoretically calculated transfer function. First, we will see the Bode plot comparison between the estimated transfer function and the theoretical transfer function. The blue line represents the theoretical transfer function and the dotted red line is the estimated transfer function. Then the step response. The blue line represents the theoretical transfer function step response and the dotted line represents the estimated transfer function step response.
So you have seen now how to find out the transfer function of a system experimentally. This completes the modeling part of this course. In the modeling, we have seen that you can find out the transfer function of a system using differential equations. You can find it out experimentally using step inputs, using frequency response, and there are other ways in which you can use both the informations. If you know the differential equation, use that as well as the experimental data to get to the correct transfer function. We have not discussed that hybrid method, but in general these are the two methods which generally works, okay, for most simple systems. So once you have the transfer function, now you can go ahead and analyze these systems. So from now on, as we move ahead in these lectures, we will assume that the transfer function is available to us, and then we will go ahead. So I'll end it here today itself. Thank you.